Hello, and welcome to Deep Sleep Science. Settle in and let your mind drift away from the immediate world around you. Let the daily noise fade into a distant hum. We are about to embark on a journey that takes us to the very limits of our understanding, to the boundaries of space and time itself. Tonight we travel into the deepest shadows of the cosmos. We travel to the heart of the enigma, the black hole. Imagine, if you will, looking up at the night sky. It is a canvas of velvet black, scattered with the diamond dust of billions of stars. Each one of those points of light is a sun, a roaring inferno of nuclear fusion, fighting a constant battle against the crushing grip of its own gravity. But there are places in that dark expanse where the light does not shine. Places where gravity has won the ultimate victory. These are the silent giants, the cosmic prowlers, objects so dense and so powerful that they puncture the fabric of reality itself. A black hole is not merely empty space, though its name suggests a void. It is the exact opposite. It is a great amount of matter packed into a very small area. Think of a star 10 times more massive than the sun squeezed into a sphere the size of a large city. The result is a gravitational field so strong that nothing, not even light, can escape. From the outside, they are invisible. We cannot see them directly, for they emit no light of their own. We only know they are there by the chaotic dance of the stars around them, or by the brilliant scream of gas and dust as it spirals into the abyss, heated to millions of degrees before vanishing forever. In this hour, we will explore the life cycle of these mysterious objects. We will stand at the precipice of the event horizon, the point of no return. We will hypothesize about what lies at the center, the singularity, where the laws of physics as we know them break down. We will contemplate the bending of time, the warping of space, and the ultimate destiny of our universe. So breathe deeply. Relax. Let us drift towards the horizon. To understand the black hole, we must first understand the star. Stars are the crucibles of the universe, grand engines of creation. Our own sun is a middle-aged star, burning steadily, fusing hydrogen into helium in its core. This fusion releases energy, heat, and light that pushes outwards. This outward pressure balances the inward pull of gravity. It is a delicate, billions-of-year-long equilibrium. A stalemate between crushing weight and explosive power. For most stars, this balance shifts gradually. When they run out of fuel, they might swell into red giants and then gently puff away their outer layers, leaving behind a white dwarf, a cooling ember the size of Earth. But for the massive stars, the true titans of the galaxy, those with 8, 10, or 20 times the mass of our sun, the end is far more violent and far more transformative. But before we delve into the cataclysmic end, let us pause and reflect on the history of this idea. It is a concept so strange that for decades the greatest minds in physics refused to believe it could be real. The story begins, not with Einstein, but nearly 2.5 centuries ago, in the candlelit study of an English clergyman named John Michell. In 1783, Michell was pondering the speed of light. He asked a simple yet revolutionary question. If a star were massive enough, could its gravity be so strong that the escape velocity exceeded the speed of light itself? He calculated that a star with the same density as the sun, but 500 times larger, would have such a pull. He called these theoretical objects dark stars, if there should really exist in nature any bodies. whose density is not less than that of the Sun, and whose diameters are more than 500 times the diameter of the Sun. Their light could not arrive at us, he wrote. It was a flash of brilliance centuries ahead of its time. But the idea lay dormant, a mathematical curiosity, until the 20th century. When Einstein published his general theory of relativity in 1915, he profoundly changed our understanding of gravity. Gravity was no longer a force pulling objects together. It was the curvature of space and time caused by mass. Matter tells space how to curve, and space tells matter how to move. Within months of Einstein's publication, Karl Schwarzschild, serving in the German army on the Russian front, found the first exact solution to Einstein's equations. He calculated the curvature of space around a single spherical mass. He found that if you squeezed that mass into a small enough radius, the curvature would become infinite. It was a singularity. Even Einstein thought this was merely a mathematical quirk, a result of the idealization of the problem, not a physical reality. He believed nature would find a way to prevent such a collapse. He was wrong. It took the work of Subrahmanyan Chandrasekhar and Robert Oppenheimer in the 1930s to show that the collapse was inevitable. Chandrasekhar, at the tender age of 19, realized that above a certain mass limit, a white dwarf star could not support its own weight. It would collapse. Oppenheimer, years before he led the Manhattan Project, calculated that a massive star, once its nuclear fuel was spent, would contract indefinitely, cutting itself off from the rest of the universe. He described it as a continuous contraction. The term black hole wouldn't be coined until the 1960s by American physicist John Archibald Wheeler, a name that perfectly captured the terrifying finality of these objects. So, we see that the black hole is not just a monster of the dark, it is a monster of history, a ghost that haunted physics for centuries before we finally accepted its existence. And now, we know they are real. We know they are out there, waiting in the dark. When such a massive star burns through its hydrogen, it begins to fuse heavier elements. Helium turns to carbon, carbon to neon, neon to oxygen, silicon, and finally, iron. Iron is the ash of stellar fusion. It cannot be fused to create energy. The fire in the core goes out. In that instant, the balance is broken. Gravity, which had been held at bay for millions of years, instantly asserts its dominance. The core, an iron sphere heavier than the sun but smaller than the Earth, collapses in on itself. It happens in a fraction of a second. The outer layers of the star invoke a bounce, triggering a supernova explosion, one of the brightest events in the universe, momentarily outshining entire galaxies. But what happens to the core? If the core is massive enough, more than about 3 times the mass of our sun, there is no force in the known universe strong enough to stop the collapse. Not electron degeneracy pressure, which holds up white dwarfs. Not neutron degeneracy pressure, which supports neutron stars. The collapse continues. The matter is crushed smaller and smaller. It shrinks past the size of a planet, past the size of a city, past the size of a pinhead. And it does not stop. It crushes down to a single mathematical point. The star has effectively vanished from the visible universe, leaving behind a gravitational ghost. A black hole is born. Every black hole is guarded by a boundary known as the event horizon. This is not a physical surface. You could not stand on it, you would not crash into it. It is a mathematical boundary in space-time, the point of no return. Imagine you are in a canoe, paddling upstream on a river. The river gets faster and faster as it approaches a waterfall. At a certain point, the current becomes faster than you can paddle. No matter how hard you stroke, you will be pulled over the edge. The event horizon is that point in the river of space. Beneath this boundary, the current of space is flowing inward faster than the speed of light. Since nothing can travel faster than light, nothing can escape. The radius of this sphere is called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who first solved Einstein's equations for a non-rotating mass in 1916, famously doing so while serving on the front lines of World War I. For the Earth to become a black hole, you would have to squeeze its entire mass into a marble about 9 millimeters across. For the Sun, the event horizon would be about 3 kilometers in radius. Once something crosses the event horizon, it is cut off from the rest of the universe. If you were to cross it, you couldn't send a radio signal back to your friends on the spaceship. The radio waves themselves would be dragged down towards the center. To an outside observer, you would never actually be seen crossing the horizon. We will discuss this strange phenomenon of time later, but physically, you pass through without a bump. It is a silent transition from the realm of the possible to the realm of the inevitable. Inside the horizon, all paths lead inward. In normal space, you can move left, right, up, down, forward, or backward. Inside a black hole, space is so twisted that toward the center becomes a direction in time. Just as you cannot stop tomorrow from coming, inside a black hole, you cannot stop yourself from reaching the singularity. The future leads only to the center. At the very center of the black hole lies the singularity. This is the heart of the mystery. According to general relativity Einstein's theory of gravity, the center of a black hole is a point of infinite density. All the mass of the star that formed the hole, and all the matter it has consumed since, is concentrated into a point with zero volume. This implies that the curvature of space-time becomes infinite. The gravity is infinite. It is a place where math gives us an error message. Divide by zero. Physicists believe that the singularity is not actually a point of infinite density, but rather a signpost that our theory is incomplete. General relativity works beautifully for large, heavy things like stars and galaxies. Quantum mechanics works beautifully for tiny things like atoms and particles. But at the singularity, we have something that is both incredibly heavy and incredibly tiny. We need a unified theory quantum gravity to describe it. We do not have one yet. Some theories, like string theory or loop quantum gravity, suggest that the singularity might not be a point, but a tiny vibrating ball of energy, or a fuzzball. Others suggest it might be a gateway to another universe. But for now, as far as classical physics is concerned, it is the end of the line. The garbage disposal of the cosmos. If you were to fall in, you would reach the singularity in a matter of seconds after crossing the horizon. But those final seconds would be interesting. Let us conduct a thought experiment. Imagine you are an astronaut floating towards a black hole. Not a supermassive one, but a regular stellar mass black hole, perhaps 10 times the mass of the Sun. As you get closer, you begin to feel the effects of tidal forces. We know tides on Earth are caused by the moon pulling harder on the side of the Earth facing it than the side facing away. With a black hole, this effect is magnified trillions of times. If you fall in feet first, your feet are closer to the black hole than your head. Because gravity strengthens so rapidly with distance, the pull on your feet is significantly stronger than the pull on your head. You feel a sensation of being stretched. At first, it is uncomfortable. Then it becomes painful. The force pulls your body into a long, thin strand. Simultaneously, because all paths converge at the center, you are squeezed from the sides. You are stretched vertically and compressed horizontally. Physicists, with a rare sense of humor, call this process spaghettification. Eventually, the forces exceed the tensile strength of human skin, muscle, and bone. You are pulled apart into a stream of atoms, a long noodle of matter spiraling into the void. It is a violent end, happening before you even cross the event horizon of a small black hole. Interestingly, for a supermassive black hole, one with the mass of millions of suns, the event horizon is much further out from the center. The tidal forces at the horizon are actually quite weak. You could cross the event horizon of a supermassive black hole without feeling anything at all. You wouldn't know you were doomed until you looked back and saw the universe shrinking into a smaller and smaller circle of light behind you. Now, let us shift our perspective. Suppose you stay on the spaceship, safely far away, and watch your robotic probe fall towards the black hole. As the object gets closer to the event horizon, you see something strange happen. Light has to climb out of the gravity well to reach your eyes. As it climbs, it loses energy. Losing energy for light means its frequency drops, it becomes redder. This is called gravitational redshift. Let us deepen our understanding of this phenomenon. Light is a wave, and the color of light is determined by the distance between the peaks of that wave. Blue light has short, tight waves. Red light has long, lazy waves. As a photon of light fights its way out of the intense gravity of a black hole, it is like a climber hiking up a steep mountain. It gets tired. It loses energy. For a light wave, losing energy means stretching out. Use your imagination to visualize this. A beam of crisp blue light emitted from a probe near the horizon. As it travels towards you, gravity pulls it back, stretching it like a rubber band. By the time it reaches your eyes, it is stretched into yellow, then orange, then deep red, and finally into infrared, radio waves, and silence. This is not just a trick of the light. It is a fundamental truth about the relationship between energy and gravity. It is the universe's way of telling us that there is a cost to escaping the dark. Nothing leaves for free. But more profoundly, time itself begins to slow down. Gravity warps space-time. The stronger the gravity, the slower time runs relative to a distant observer. As your friend falls, their movements appear to slow down. They wave their hand, and it takes minutes for the wave to complete. Then hours. Then years. As they approach the very edge of the horizon, they appear to freeze. You never actually see them verify across the horizon. Their image just becomes redder and dimmer, freezing at the edge of darkness, fading into invisibility over infinite time. They become a ghost, plastered on the surface of the void. But from their perspective, time runs normally. They look at their watch. The second hand ticks at 1 second per second. They look out at the universe, and depending on the geometry, they might see the outside world fast-forwarding, eons passing in the blink of an eye. They cross the horizon and hit the singularity in what feels like moments. This is the relativity of reality. Two observers, one falling, one watching experience. Two completely different histories. Both are correct. Disagreement is built into the fabric of the universe. While stellar mass black holes are the scattered remnants of dead stars, there exists another class of monster, the supermassive black hole. These giants reside in the centers of almost every large galaxy, including our own Milky Way. Our local giant is called Sagittarius A. It sits 26,000 light-years away in the direction of the constellation Sagittarius. It contains the mass of 4.1 million suns packed into a space smaller than the orbit of Mercury. How these monsters formed is still a subject of debate. They may have started as smaller seeds that gorged on gas and stars for billions of years, growing fat on the galaxy's lunch. Or they may have formed from the direct collapse of massive gas clouds in the early universe, before stars even existed. The most famous image of a black hole, captured by the Event Horizon Telescope in 2019, is of the supermassive black hole in the galaxy M87. That object is a true leviathan. It is 6.5 billion times the mass of the Sun. Its event horizon is larger than our entire solar system. These supermassive holes are often the engines of active galactic nuclei. When they feed, they are messy eaters. Gas swirls around them in an accretion disk, spinning at nearly the speed of light. Friction in the disk heats the gas to millions of degrees, causing it to shine brighter than the rest of the galaxy combined. They can launch jets of particles thousands of light-years into space. It is a paradox that darkest objects in the universe are capable of generating the brightest lights in the universe. We orbit Sagittarius A peacefully. We are far enough away that we are in no danger of falling in. We are merely caught in its gravitational embrace, circling it along with 200 billion other stars, a vast cosmic carousel. But Sagittarius A is just one of countless millions. Let us journey outward to visit some of the other famous residents of the Dark Zoo. We travel 6,000 light-years away to the constellation Cygnus, the Swan. Here lies Cygnus X1, one of the first black hole candidates ever discovered. In the 1960s, X-ray astronomy was in its infancy. Detectors launched on rockets found a brilliant source of X-rays in Cygnus. But when optical telescopes looked at that spot, they saw only a large blue supergiant star, HDE 226868. This star was whipping around something invisible every 5.6 days. By analyzing the motion of the blue star, astronomers calculated that its invisible partner had to be about 15 times the mass of the Sun. Too heavy to be a neutron star. It had to be a black hole. Imagine the scene at Cygnus X1. You have a massive, blindingly bright blue star, 20 times larger than our Sun. And locked in a deadly dance with it is a tiny, invisible point of darkness. But the darkness is not silent. It is stripping the outer atmosphere of the blue star. A river of superheated gas flows from the star to the black hole, spiraling inwards. As the gas falls, it scrapes against itself, friction heating it to millions of degrees, screaming in X-rays before plunging past the horizon. It is a cosmic vampire, feeding on the lifeblood of its companion. Now, let us travel much, much further. 55 million light-years away to the heart of the galaxy, Messier 87. This is the home of Pauahi, the supermassive black hole imaged by the Event Horizon Telescope. If Cygnus X1 is a vampire, M87 is a god. It is a monster of truly incomprehensible scale. To orbit M87's black hole once, even at the speed of light, would take days. Its accretion disk is a maelstrom of fire large enough to swallow our entire solar system many times over. And from its poles, it launches a jet of high-energy particles that spans 5,000 light-years, a blowtorch cutting through the galaxy. This jet travels at 99% the speed of light, visible from across the universe. It is a reminder that black holes are not just sinks of matter. They are the most powerful engines in existence, converting mass into energy with an efficiency that makes nuclear fusion look like a matchstick. And what of the middle, children? For a long time, astronomers found only small stellar black holes and giant supermassive ones. There was a gap. Where were the intermediate mass black holes? The ones with hundreds or thousands of solar masses? Recent evidence suggests they are hiding in globular clusters, ancient, dense balls of stars floating in the halo of our galaxy. In these crowded environments, stars might collide and merge, building up larger and larger black holes. These intermediate wonders are the missing link, the stepping stones between the death of a single star and the anchors of galaxies. They are out there, elusive and shy, bridging the gap in the cosmic family tree. We now touch on one of the deepest problems in modern physics, the information paradox. In quantum mechanics, information is never lost. If you burn a book, in principle, if you collected every molecule of ash and every photon of light, you could reconstruct the book. The information is scrambled, but it still exists. But black holes seem to violate this. If you throw a book into a black hole, it crosses the horizon and is seemingly gone. If the black hole eventually disappears, where did the information go? Did it vanish from the universe? Stephen Hawking famously bet that information was lost. But later, physicists developed the holographic principle. This mind-bending theory suggests that the information about what falls into a black hole isn't lost inside volume. Instead, it is stored on the surface area of the event horizon. Like a hologram, where a 2D surface encodes a 3D image, the 2D surface of the black hole might encode everything inside it. This idea has its roots in the study of entropy. Entropy, in simple terms, is a measure of disorder or the amount of hidden information in a system. Jacob Bekenstein, a graduate student of John Wheeler, proposed that a black hole's entropy was proportional to the area of its event horizon. This was a radical idea because it connected thermodynamics, the study of heat and energy, with gravity. It implies that the bits of information that make up you, me, and the spaceship are plastered onto the shell of the black hole, scrambled but preserved. If you were to look closely at the horizon, you might see a chaotic pattern of Planck-sized pixels, encoding the entire history of everything the black hole has ever swallowed. This leads us to an even stranger possibility: wormholes. Einstein's equations allow for a solution where a black hole connects to another point in space-time, a bridge, or an Einstein-Rosen bridge. In science fiction, these are the highways of the universe, allowing instant travel between stars. You fly into a black hole and pop out of a white hole in another galaxy. A white hole is the theoretical reverse of a black hole. While nothing can escape a black hole, nothing can enter a white hole. It spews matter and light out, but refuses to let anything back in. Mathematically, they are valid, but we have never seen one. In fact, the laws of thermodynamics suggest that white holes might be unstable. If a single speck of dust were to fall towards a white hole, the instability might cause it to collapse instantly into a black hole. But what if the bridge is traversable? Kip Thorne, a Nobel laureate who consulted on the movie Interstellar, calculated that to keep a wormhole open, you would need exotic matter with negative mass to push the walls of the tunnel apart. We have no evidence that such matter exists in sufficient quantities. But if it did, a black hole could be a doorway. Imagine falling in, expecting death, but instead seeing the sky above you unwrap and change. The singularity, instead of being a crushing wall, becomes a throat. You pass through exotic energy holding the gravity at bay and emerge. Where? The Andromeda Galaxy? The distant past? A parallel universe? The connection between black holes and time travel is not just fantasy. Because time slows down near the horizon, a black hole is a natural time machine to the future. If you could orbit just above the event horizon for a year and then return to Earth, thousands or millions of years might have passed at home. You would be a traveler from the past, stepping into a future you do not recognize. But traveling back in time? That is far more difficult, fraught with paradoxes. Yet some solutions to the equations of spinning black holes, curved black holes, suggest paths that loop back in time. Closed time-like curves. Whether nature actually allows you to walk these paths is a question we cannot yet answer. The universe seems to protect its timeline, but inside a black hole, the rules are rewritten. This has profound implications. If the physics of a black hole can be described by its surface, maybe the universe itself is a hologram. Maybe we are all just 2D information painted on a cosmological horizon, projecting the illusion of a 3D reality. It is a thought that keeps physicists awake at night. Black holes are not truly black. In 1974, Stephen Hawking used quantum field theory to show that black holes should emit a faint radiation. In the vacuum of space, virtual particles are constantly popping into existence and annihilating each other. Particle and antiparticle pairs appear, borrow energy from the vacuum, snap together and vanish. But right at the event horizon, a strange thing can happen. One particle might fall in, while its partner escapes. The escaping particle becomes real radiation, Hawking radiation. The energy for this particle has to come from somewhere. It comes from the mass of the black hole. The partner that falls in effectively has negative energy, subtracting from the black hole's mass. This means that black holes are slowly evaporating. Very, very slowly. For a black hole the size of the sun, the temperature is 1/1,000,000th of a degree above absolute zero. It loses mass slower than a snail moves. It would take 1067 years to evaporate, far longer than the current age of the universe. But for smaller black holes, the process is faster. As they shrink, they get hotter. In its final moments, a black hole would shine brilliant white that explode with the force of 1,000,000 nuclear bombs. Let us cast our minds forward. Not years, not centuries, but eons. Eventually, all the stars will burn out. The galaxies will drift apart. The universe will go dark. We will enter the black hole era. In this distant future, 10-40 years from now, the only things left will be black holes and stray particles. The black holes will reign supreme over a cold, dead cosmos. They will orbit each other in the dark, occasionally merging in bursts of gravitational waves. But even they are not eternal. As we learned, they evaporate. One by one, over timescales that defy human comprehension, the black holes will shine their last light and vanish. The supermassive giants will be the last to go, evaporating in flashes of light that illuminate the nothingness for a brief instant. And then, nothing. Just a bath of photons and leptons cooling towards absolute zero, stretching out into an ever-expanding void. This is the heat death of the universe, a state of maximum entropy. But wait. Before we resign ourselves to the heat death, there is another mystery to explore. A mystery that takes us back not to the end of time, but to the very beginning. We have spoken of stellar black holes formed from dying stars and supermassive ones grown in galactic centers. But there is a third kind, purely theoretical yet potentially ubiquitous, primordial black holes. In the first fraction of a second after the Big Bang, the universe was not a smooth sea of energy. It was a chaotic, boiling froth. Quantum fluctuations created tiny pockets of higher density. Stephen Hawking and others suggested that some of these pockets might have been so dense that they collapsed directly into black holes. These would not be monsters. Some might be the size of a mountain, yet weigh as much as the Earth. Others might be as small as an atom, yet weigh as much as a mountain. If they exist, they could solve one of the biggest embarrassments in astrophysics, dark matter. We know that 85% of the matter in the universe is invisible. It doesn't emit light, but it has gravity. It holds galaxies together. For decades, we have searched for exotic particles, WIMPs, axions to explain it. We have found nothing. But what if dark matter is simply a swarm of billions of tiny, ancient black holes? They would be invisible. They would be heavy. They would pass through our solar system without us noticing unless one struck the Earth directly. It is a tantalizing theory. We are looking for ghosts, and maybe the ghosts are simply the ashes of the Big Bang itself. And how do we listen to these ghosts? For most of human history, astronomy was a silent movie. We looked at the universe. We saw light. But in 2015, everything changed. We gained ears. On September 14, 2015, two detectors, one in Louisiana, one in Washington State, picked up a signal. It was a tiny distortion in space-time, a ripple smaller than the width of a proton. It was the sound of two black holes, 1.3 billion light-years away, colliding. Imagine two black holes, each 30 times the mass of the Sun. They've been orbiting each other for millions of years. As they spin, they drag space-time around them, creating waves like a boat in water. These waves carry away energy. So the orbit shrinks. They get closer. They spin faster. Faster. Closer. In their final moments, they are spinning around each other hundreds of times per second. The fabric of space is being churned into a frenzy. And then contact. They merge into a single, larger black hole. In that split second of merger, they release more energy than all the stars in the observable universe combined. But they do it in silence, in darkness. The energy is released as gravitational waves. These waves traveled for 1.3 billion years. They passed through galaxies. They passed through stars. Finally, they passed through the Earth. As they did, they stretched and squeezed the planet by a fraction of a hair's width, and we felt it. The signal was a chirp, a low hum rising rapidly in pitch whoop, and then silence. Since then, LIGO and Virgo have detected dozens of these mergers. We are hearing the universe hum with the collisions of invisible giants. We are building a map of the graveyard of stars, not by seeing the bodies, but by hearing the thuds as they fall into the grave. This leads us to a more troubling thought. A paradox within a paradox. The firewall. We mentioned earlier that the event horizon is a no-drama zone. According to Einstein's equivalence principle, falling freely through space should feel the same regardless of where you are. Falling through an event horizon should feel just like floating in deep space. You shouldn't notice anything special until it's too late. But in 2012, a group of physicists realized that this smooth ride contradicts the principles of quantum mechanics we discussed earlier, specifically the conservation of information. If information is preserved, then the particles radiating from the black hole must be entangled with the particles that fell in. But they must also be entangled with the particles that radiated away in the past. In quantum mechanics, a particle cannot be fully entangled with two different things at once. It's called monogamy of entanglement. To fix this, the entanglement between the infalling particle and the black hole must be broken just as it crosses the horizon. Breaking entanglement releases energy. A lot of energy. The calculations suggest that this energy would form a wall of fire at the event horizon. A literal firewall. If this is true, then falling into a black hole is not a peaceful drift into darkness. It is an instant incineration at the surface. You hit a wall of pure energy and are vaporized before you even enter. This breaks general relativity. It says Einstein was wrong about the equivalence principle. But if we keep Einstein's smooth ride, we break quantum mechanics. Physics is stuck. We have to choose. Is the horizon a smooth path to nowhere or a burning wall of death? We do not know. The black hole guards its secrets well. And what of the future? What of our relationship with these objects? For now, we watch from afar. But one day, humanity may need them. Bremen Dyson, a visionary physicist, speculated that an advanced civilization could build a shell around a star to harvest its energy or Dyson sphere. But a civilization living in the black hole era, long after the stars are dead, would need a different power source. They could build a Penrose sphere around a rotating black hole. By dropping garbage into a spinning black hole and letting it scatter off the rotation, you can steal energy from the black hole's spin. You can slow it down and extract the energy of 1 billion suns. A city built on a ring around a black hole could live for eons, powered by the dark engine in the center. They would overlook the accretion disk, a permanent sunset of swirling plasma. They would see the universe warped into a funhouse mirror by the lens of gravity. They would live on the edge of the ultimate precipice, warm and safe, fueled by the very thing that consumes all. It is the ultimate survival story. Life clinging to the edge of death. Finally, we must acknowledge the shadow these objects have cast over our own collective psyche. Before we knew they were real, they were the monsters of our nightmares. In the 1979 Disney film, The Black Hole, they were depicted as a gateway to hell, a place of ultimate judgment. In Star Trek, they were hazards to navigation, anomalies that destroyed time. But in 2014, Christopher Nolan's Interstellar changed everything. For the first time, a black hole gargantua was simulated with real physics. Kip Thorne provided the equations. The result was not just a movie monster, but a thing of terrifying beauty. The glowing ring of the accretion disk, bent over the top and bottom of the shadow by the lens of gravity. It showed the world what we have been discussing tonight, that black holes are not simply holes. They are spheres. They are three-dimensional objects in a four-dimensional universe. They represent the ultimate unknown. In a world where we have mapped every continent and explored every ocean, the black hole remains the final frontier. It is the dragon on the edge of the map. Here be dragons, and just like the dragons of old, they inspire fear, yes, but they also inspire wonder. They remind us that the universe is far stranger, far more powerful, and far more beautiful than our small human brains can easily comprehend. They humble us, and in that humility we find a connection to the infinite. It is a somber thought, but there is beauty in it too. It highlights the preciousness of this moment. We are living in the stelliferous era, the era of stars. The only time in the history of the universe when life as we know it is possible. We are the universe waking up and looking at itself, marveling at its own monsters before the lights go out. As we return to the present, to our small blue planet orbiting a yellow dwarf star, we can look up at the blackness of the night sky with new eyes. The dark is not empty. It is textured. It is heavy. It is hiding giants. Black holes are the ultimate laboratory of physics.